Hi, and welcome to the Origins Podcast. One of my favorite parts of the month is What's New in Science with my friend and colleague Sabine Hossenfelder, who's here today. And we, as usual, talk about what's new in science this month and the past month. Sometimes things that are hyped, sometimes things that are actually exciting. It depends. It's been kind of a slow month, as Sabine and I were talking about beforehand. I don't know if it's because it's the end of the school year in the Northern Hemisphere, at least, or whether it's because of all of the government cutbacks and concerns about what's going on and people are holding off writing up, or if it's just an accident, which is probably the answer. I don't have any real ideas about that. I don't know if Sabina, if you have any, but it is a slow month. You would agree?
Yeah, these things just happen, like, it comes and goes.
Yeah, you can't control discovery. Anyway, so we have, as usual, the format we established a few months ago. We have 6 topics, and and Sabina will lead off.
Okay, so, I'm going to start with, something that's between hype, and actually exciting. So it did get a few headlines, but not too many. It's a way of creating electricity from rain, and I think one of the headlines I saw was that it's going to overhaul the power grid or something, and it's like a new form of renewable energy and so on. So I looked at the paper fully expecting this to be complete nonsense, but it's not that bad. I actually think it's kind of interesting. It's just
Yeah.
that, it's not as big as the headlines made it sound. So what they did was they, took small plastic tubes basically and let water run through them. So normally you can't create electricity from that because, as I learned, what happens is that you get, a polarization building up, between the fluid and the plastic, but the charges don't move. So they just get stuck to the wall of the plastic tube. So if the charges don't move, you can't create electricity from it, so that's bad. So what they did was something different. They took water drops, and air in between them. And what happens then is that the water kind of it pulls the charges with it. So now you actually do have charges flowing, and you can create electricity from that. And they did this, in the laboratory, for, a couple of those, straws, and they pumped a certain amount of fluid through, and they actually ran some tiny LEDs with it, and they measured the power output. And so, this is all well and fine. So what they got was, something like zero point 0.4 milliwatt per, these straws, but they were really tiny, like 2 millimeters in diameter. And what they did then was they said, "Well, we could just stack them next to each other." So we have like a plate or something of these, straws, and then we catch rain on it, and that would create 100 watts per square meter. It was like 100 watts per
Yeah.
square meter. This is like not so far off, like it's maybe a
Yeah.
factor 5 to solar
Mm.
panels or something. Like this is
Yeah.
like I was like, this can't possibly be. Like there isn't that much gravitational energy in rain. So I looked at the paper, I got very confused about this, but after some time, I realized that their calculation is perfectly correct, but the amount of rainwater that you would need for that is something like 20,000 liters per minute. And I calculated this in the way that rainfall is usually measured, like in millimeters per hour or something like
Yeah.
that, and you would need kilometers per hour
Yeah.
for those 100 watts. A reasonable amount, to produce is something in the range of a few milliwatts, from rain. So, it seems to work. It looks plausible, and their experiments look, convincing to me. I mean, it's not that I checked the experiment, but it looks all fine, but it's not going to revolutionize the power grid.
Yeah, no, when I first heard it, I was dubious, as you were, and then I looked at the reports about it, and it was, I mean, it's basically the idea of like dragging your hands across. I mean, you're just the water, the raindrops, because they're individual, somehow drag the charge, like, it's static electricity, like when you rub a balloon on a wall and you can hold it up. Um, and and the interesting thing, of course, is they point out that the drops that are needed. A continuous fluid won't do it. You need the drops. Yeah, and so my first thought was, yeah, it's cute. But one number that was quoted, and I don't know, which was maybe the paper described in more detail. I was a little confused. It said 20 seconds of rain would power 12 LED light bulbs. Um, Now, one thing I didn't say, will power them for how long? A fraction of a second, or the 20 seconds, and so I was highly dubious about that statement. I assume it would mean they would provide enough power to light up a light bulb for some short time. But do you know if that was in the paper at all?
I didn't see it in the paper. I looked at the stuff with the, amount per square meter. So
Yeah.
I didn't look at the time because as you point out, like, it's not particularly meaningful. Like,
Yeah,
yeah.
exactly. So
Uh,
I was when I saw that, I thought, okay, well, whatever that is, that's an overestimate because I'm sure it isn't powering 12 LEDs all the time, or indeed, this would be a revolutionary technology in a sense. Of course, it depends. If you needed a kilometer to power 12 LEDs, it'd be a different thing. It didn't say how much rain, how much area, as you point out, and how much rain is coming down. It's kinda cute, and, they did make it sound like this would be useful in sort of areas where there isn't a grid, and I'm dubious. Of course, the big question is always the same thing they do about rain or sun, but in this case, worse. It has to be raining for it to work. So you don't get I mean, in terms of a, useful power source, um the relying on bad weather to have power is an interesting concept. But nevertheless, as a proof in principle, it's kind of neat, and it certainly doesn't violate any laws of physics, which is always surprising when it sounds like you're getting something for nothing. In this case, you're getting very little from something. Would you say that?
of course, if you want to generate electricity from rain, you could just take a rain pipe and put a turbine into it, and it's actually more efficient. I looked it up in converting the gravitational energy in the rain into electricity. It's just that the nice thing about their idea is you don't need the turbine, so you don't have any moving parts. So you can
Yeah,
just
that's the
take the thing
point.
and
You don't
put
have
it somewhere. Yeah.
Yeah, when I first saw it, I thought, "Okay, yeah, that's what they're doing. They're doing a turbine." But the point is, if you don't have a turbine and you just have some straws, it's nice, um, at least in principle, right, to not have moving parts. And in principle, it's nice to look for. I do like the idea of looking for power generation places where you don't need a lot of infrastructure. But anyway, this is more cute than anything else, and I enjoyed learning about it. It would surprise me. I'm still dubious, as you say, about some of the claims, but it's interesting. And it's not, as you said, somewhere between hype and exciting in the sense that it works, it's real, it's it's not false. Speaking of hype, let's go to the next topic, which I think gets the Hype of the Month award, and it isn't related to quantum computing to this month or anything like it, but it's the other subject where there's always hype, which is astrobiology. In every paper, I remember seeing the front page of the New York Times, earlier in the month, there was a statement that there were now, using the James Webb Space Telescope, there were claimed the strongest hints yet of biological activity outside our solar system, quote unquote. Claims of biosignatures on some planet K2-18, a sort of small Neptune-like 9 times the Earth planet, about 38 parsecs from the Earth. And of course, this caused anytime there's a claim of potential life elsewhere, it's all over everywhere. And every time there's such a claim, it's almost always wrong. And either hyped or wrong. And in this case, I think it's a combination of both. Um, this was a group. So the claim was that with JWST, by looking at the light from the star going through the atmosphere of the planet, you can then look at spectral lines, a standard way to look at atmospheres. And there was a claim of a discovery of dimethyl sulfate, dimethyl sulfide, which is interesting in principle because dimethyl sulfide is one of the things that's produced by marine phytoplankton. And so if there are oceans in this planet, marine phytoplankton could produce it. And there's also dimethyl disulfide, which is another thing that marine planktons produce. So lots of excitement. Now, the problem. First of all, this is a group out of Cambridge. First of all, this Cambridge group made the same claim in 2023, and subsequent analysis showed no signs of that at all of that signal. In a separate independent analysis saw no signs of those kind of lines in the spectrum. But it gets
Was
worse.
it the same planet in
Yeah, yeah,
2023?
yeah, 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 yeah. The claim in
Okay, well,
2023
that's weird.
was debunked. So the same group suddenly says, "Okay, we've got new data," and and it's even worse actually, um, because first of all, the actual looking at at that atmosphere of the planet, m many analyses would suggest a planet that big, far away, would not have water, would not have liquid water, which is kind of the thing you'd look for if you have marine phytoplankton. And so the theoretical estimates were this is gonna be a barren planet. Well, in fact, looking at the atmosphere of the planet, all signs are that there's no water vapor in it. In fact, all the signs are that it is a barren planet. So the actual experimental data confirms the theoretical expectation that there's no water on the planet, first of all. Secondly, yet again, a new group looked at the same data, noisy data at the limits of resolution of the JWST. It was a kind of a 1 sigma claim originally. Looked at the data, but not looking for dimethyl sulfide, not sort of, not determining in advance what you're looking for, but just doing a kind of blind analysis, found no evidence of the spectral lines. And finally, it turns out bimethyl sulfide is not necessarily produced by biology. It's observed in the molecular clouds and in the interstellar medium. So in almost every way, this is no evidence for life on this planet, in spite of the fact that it got the headlines in every paper. Once again, reminding us that one needs to take claims of life elsewhere in the universe and most claims of astrobiology with uh, enough salt that it could be dissolved by the kilometers of rain that are needed to make enough power from that last experiment.
Yeah,
Anyway.
it's like the phosphine on Venus story,
Yeah,
right?
yeah,
Right,
it's
yeah,
but
yeah.
this is, I think, even worse because this group has a history. I asked a co When I first saw it, I asked a colleague of mine, who would just one of the first people to discover exoplanets, and he said, "This group has a history of making these claims. I'm a little dubious." And then it turns out, so are all the other scientists. So after the announcement, there were many articles, but of course not in the New York Times. The newspapers never publish the counterclaims after they've made some exotic claim. But in Nature and everywhere else, we're going over all the other planetary scientists who've argued that this is not a sign for a host of number of other reasons. Nature and many other are, and as I say, another independent analysis. So, Hype of the Month award goes to that amazing claim that, of course, we'll hear about it all the time that biosignatures have now been discovered in other exoplanets. Anyway, let going from hype to something that I think is doesn't even rise to the level of hype. Um, you have something about gravity you wanna talk about.
Yeah, so I would say it's an attempt at hype, and not the first one coming from this person, as I realized later. So it's some physicist who claims that the universe is a computer simulation, and the evidence for this is gravity, because gravity is really a computation. And he's got the maths to show it, and I looked at the maths, and I wasn't very convinced by it. I actually think it's bluntly wrong. But what I thought was interesting, which is why I thought we could talk about it, is that he tries to connect this idea to Eric Verlinde's idea of entropic gravity,
Yeah,
which attracted a lot of attention, like 2011, so quite a while ago.
yeah,
So Verlinde's idea was that you can describe gravity as basically the increase of entropy of something.
yeah,
And he seems to have strings in mind, maybe because his brother is a string theorist. But it wasn't actually necessary to do the calculation, and it didn't really play any role, so you didn't really know what this underlying microscopic thing is that has entropy. And so the new author tries to fill this in by saying, well, the universe is a computer, so it's made of pixels, and the pixels are the underlying microscopic thing. And then he calculates the entropy, and I think the sign is just wrong, and he doesn't really understand how you calculate the information of a bit string. But that's kind of tangential. So I still think, and I looked at Verlinde's paper when it came out in quite some detail, and I think it's mathematically correct. You can reformulate gravity, at least on the Newtonian limit, so it's not fully
Yeah.
generally covariant, as a thermodynamic theory, which in itself is quite interesting. But we don't know what this underlying stuff is. I find this interesting because we might have talked about this at some point. There's this question like, do gravitons exist?
Yeah.
Right. So the quanta of gravity. If you believe that gravity has to be quantized, they should exist. However, on the other hand, there's the idea that it doesn't make any sense to actually quantize gravity because it'd be like trying to quantize water to get water molecules. That doesn't make any sense, right? So you need to know what the underlying thing is, and then you
Mm.
derive gravity in a classical limit.
Mhm.
It doesn't have any quanta. And so I think that Verlinde's idea is one of the clearest examples of this, which is already kind of damning, I guess, seeing how unclear it is. But yeah,
Well, I mean, I'm a little confused about what before we get to this paper, which seems to me to be complete nonsense. Personally, having at least I haven't read the paper. I've read the description of the paper, but even that makes me highly dubious. But look, I mean, if there are gravitational waves, we know there are gravitational waves, and we do know that if you take that the variables of gravity are space and time, and if you quantize them, you can get out gravitons, and you get a perfectly you get a theory which has these fundamental particles, but that theory doesn't make sense. But so I don't quite understand. I mean, you sh you quanti you I guess what you're saying is if there's some more fundamental theory, what is the quanta of that theory? But certainly, if you just take gravity itself, the fundamental quantized objects are space and time, right? You're quantizing space and time,
yeah,
and
yeah.
if you just go ahead,
Sure, you
finally,
can do this, but just because you can do it doesn't mean it's actually correct.
oh yeah, well, I mean, you can do it, and when you do it, you come up with ultimately mathematical nonsense, which is the problem, right? I mean, you can get a theory that
Well,
produces
yeah.
infinity.
Well, I would say, like, what you get, might be a good approximation. So it breaks down, a strong curvature regime, like, this is unfortunate because exactly the places where you would like to have a theory of quantum
Y
gravity, like inside
yeah.
of black holes at the Big Bang or something, you can't use it because it doesn't work. But in the if gravity is weak, which, around us, it's all the time, basically, then this approximation with the gravitons should work.
Yeah, sure, and it
Yeah.
should reduce, and it does ultimately reduce to classical gravity, just like, you know, quantum electrodynamics, and in its simple in the simplest version without higher order corrections reduces to electromagnetism. But yeah, I mean, it should work. And by the way, I'm betting gravitons exist, and that's why with as you know, I think that with our old friend and my old collaborator Frank Wilczek, we showed something that I think is fascinating, that if there are gravitational waves from inflation that are ever discovered, that will be direct evidence that gravity is a quantized theory, that there are gravitons. And I think that would be remarkable. It would, of course, be remarkable for other reasons to discover gravitational waves from inflation. It would show that inflation happened, among other things. But yeah, but this is the big question. But so that's a fundamental question of interest. But there are two there when I read about this, there were two things that immediately my antenna went up, and I looked at the past research of this researcher. And first of all, he's published research suggesting that information has mass, which is not, I mean, I manifestly seems false, because photons carry information. They don't have mass. They carry energy and momentum, but they don't have mass, but they certainly carry information. So I don't understand that. And he's also suggested something that sounds very Deepak Chopra-like, that all elementary particles store information about themselves the way cells do. And so all of this strikes me as a little weird. I mean, certainly both of them are manifestly, as far as I can tell, incorrect. At least the first one is just wrong. The second one, there's no evidence that elementary particles carry information about themselves in any sense that I know of. So when I read about, if those are accurate representations of the earlier work, then the new work is sort of suspect.
Yeah, I'm afraid that's the case. Actually, when I was reading the paper and I came to the conclusion, I think that's just wrong. Like the way that he calculates the information of this distribution of points or something. And then he wants to argue that information decreases when matter clumps because information decrease is the same as entropy increase. So
Oh,
so so that's, the kinda, but it's just not the case, actually.
yeah, yeah,
Entropy normally does decrease, if you clump things because then there's less that you need to store, like
yeah, yeah.
yes, so I think he just has a sign mistake in his equation and that, you know,
The
swaps
famous
an
sign
increase into a
error.
decrease. Yeah, but so I realized that he tried several years ago already to make this claim that we live in a computer simulation because of something with information. And so I just find it interesting that this idea that we live in a computer simulation, uh, you know, it seems so appealing to some people.
Yeah, everyone seems to like it. They quote Elon Musk, but of course that doesn't do much for me anymore. But I don't know why people are. I understand the Matrix was fun series of movies, but I don't understand why the idea that we live in a matrix is so appealing. There's no evidence of it that I can, and as far as I can think of it, there's manifest other non-evidence. The best non-evidence is that, as far as I know, in simulations, are usually pixels that fail. As far as I know, we don't generally find them around the places where the laws of physics fail. But and then it doesn't answer the fundamental question. I mean, somehow it's like, oh, well, that explains why we live in a complex universe, but it means that there's something more complex that created us potentially. But then it does. What? Who created that? Is that a simulation? And yet, is it simulations all the way down? So you don't find the idea attractive either, I gather?
I find it quite useless. Like, so
Yeah.
so to me, it's kind of like it's an approach at the theory of everything. This is how I
Yeah.
think about it. Because if you could give me the algorithm and it would actually predict everything we see, that would be great.
Yeah.
So where's your algorithm? Well, the people who like the idea don't have it. Like, this is also why I looked at the paper because, maybe I thought maybe he's figured something out.
Yeah.
But yeah,
It
so it's and they always come up with some kind of weasel words, about how, if no one looks at a particular part of the universe, then you don't have to do the calculation, so you can save a lot of computational power. And I'm like, well, how do you know that no one looks? And what do you do if someone looks later?
yeah.
Right? So then what? So that doesn't make any sense to me. It's all very vague and fudgy. And you
Yeah,
could also ask,
loosey-goosey.
like, so if it's, there's this whole question about a quantum computer, right? So we do observe quantum effects.
Yeah.
So is it a classical computation or is it a quantum computation? If it's a quantum computation, then how do you get classical chaos? Because for that you need nonlinearity, right? How do you work it out? Like, and I never get any answers to this.
Yeah, never get, because in principle, the other yeah, you hit another neat point. I mean, if some people say, well, it's, a matrix simulation will be indistinguishable from the universe in which we live. Well, if it is, then A, there's no way to know, right, from a physics perspective, and B, big deal. I mean, what physics is about is to try and figure out the universe we live in. If it's a simulation, who the hell cares? We're trying to figure out the laws that govern the experiences we have, and it doesn't change anything. And so it doesn't change anything, and I think it's poorly motivated. It doesn't resolve problems of how we come in a complex universe. In fact, in my mind, it makes it worse. But people love it, and I guess it's good science fiction. But okay. Well, now I want to move to something that isn't real hype. It's not uninteresting, and I wanted to bring it up for a number of reasons. This is some experiments at the Large Hadron Collider, and it's a recent report about evidence for exotic antimatter nuclei in heavy ion collisions at the LHC, with an experiment called the Alice experiment. And heavy ions, so the LHC can be used for for accelerating protons around, but it can also be used to accelerate ions, complex, like gold or lead or whatever, and smashing those things together. And the advantage of that is you have a much bigger system with lots of particles. And if you're trying to recreate conditions in, say, neutron stars or even in the early universe where you have enough particles to have something that looks like a thermal, situation with enough particles interacting, you might be able to learn about the conditions of matter under high temperatures or densities, and that's personally reasonable. And so they quote the discovery of an anti-hyper helium-4 nucleus. Um, Hyperons are like protons. Protons have up and down quarks, and in hyperons, one of the down quark is replaced by a strange quark. So it's an exotic partner of the proton, and these are created in collisions, and they're obviously unstable for a little while, but they exist, and and so previously, the interesting thing is to see not just creating antimatter. When you slam particles together, you make antiparticles, but there have been anti-nuclei that have been observed. There's been the anti-neutron. There's an anti and anti-hyperons, and then there's even been anti-deuterons, I think, been observed, and anti-hyperon deuterons, where one of the protons is replaced by a hyperon. So this is a 3 sigma observation of anti-hyperhelium, which has 2 antiprotons, 1 antineutron. So helium, it's got 2 protons and 2 neutrons. So anti-helium has got 2 antiprotons and 2 antineutrons, and it's amazing that can be created. But this is even more exotic. It's got 2 antiprotons, 1 antineutron, and 1 antihyperon. And so you might say, great, but big deal. In fact, if you're Sabine Hossenfelder, you might say that. So, but the reason I wanted to bring it up is that what it illustrates is that these systems at high pressure and temperature, the early universe and neutron stars, have a lot of exotic stuff. And it's not, and it's important to realize that when we're trying to understand those conditions in those systems, that you can't discount, that basically anything that can be created is created, and all of these exotic things can contribute to this bath, this soup, primordial soup. And, that may or may not be relevant to one day trying to understand the properties of those systems. And so it's not uninteresting that you can at least create that. This just gives further evidence that these systems that at high temperatures and densities, you get really exotic stuff, and that may be relevant someday. So that's why I thought I'd bring it up.
Yeah, well, so I wouldn't dare say it's totally uninteresting. I mean, so first of all, I already think it's interesting that you can actually create bound states with those strange quarks in them. So
Yeah.
normally they don't exist in the world around us because they're unstable. So normally in the stuff around us, we only have the 2 lightest quarks, the up and down quarks, as you said, and the strange quark is the next heavier one, and that makes these things unstable. But so in those particle collisions, you can create all kinds of stuff with the strange quarks in them. And so one of the reasons I think it's interesting, and I think a lot of people don't really appreciate that, is that if you want to make predictions for the Large Hadron Collider, the higher the energy, the easier the prediction in some sense, because the strong nuclear force becomes easier to calculate the higher the energy. So that's a little counterintuitive. And if you want to accelerate these larger heavy ions, I forgot what do they take, gold, lead, or something like that,
Yeah.
something big, um, then you distribute the energy from the acceleration over all the constituents.
Yeah.
So the energy in the individual nuclear collisions is much smaller. Um, in this kind of range, it's actually quite difficult to predict exactly what's going to happen. And this is what makes this so interesting. You actually have to go and measure it, like what actually happens. You kind of said, like, you have this thermalized ball of nucleons. I think it's actually somewhat controversial if it's actually thermalized. Like,
Yeah.
this is where the problems start. And then you don't really know what's the probability of creating all these things, how do they behave, and so on and so forth. So these I forgot what it's called, the helium hyperon, whatever the complicated things with its
Anti-hyperhelium-4.
anti-hyperhelium 4. Exactly. Um, so it has a lifetime of 200 picoseconds or something. So it's
Yeah.
basically
Yeah.
gone immediately. So you can't do anything with it, but it teaches you something about nuclear physics,
Yeah.
which we still can't really calculate.
Yeah, I think, and so, and you really hit the point in the nail on the head there. I think that in these complex systems, you can do calculations and you can try and do some tricks with QCD with the strong interaction at high temperatures, and been involved in some of that early on. Um, but of course, it's a complicated system and you want to measure it. And if you really want to try and understand these thermal systems, we often say, and I know you say it's hype, that when one is using, the LHC one is, recreating the conditions of the earliest moments of the Big Bang. Not quite, because, the Big Bang was a thermal system with lots of particles, and you're hitting two protons together. But you can try and do better with these ions, and at least try and get some sense of the thermal conditions, which, as I say, is not just relevant for the Big Bang, but also relevant for neutron stars, which is relevant for us because, in the creation of a neutron star, all of the all probably many of the heavy elements that now exist on Earth were created, and so it's nice to do the experiment, and it is kind of amazing, nevertheless, even though it exists for a few picoseconds, still it's kind of amazing that you can create an anti-nuclei that's that big, not just anti-helium, which itself is kind of amazing, but anti-helium, where one of those bits is replaced with something even more exotic. It's kind of and that you can actually measure it in that morass, which is always amazing to me as a theorist, that people can actually go into that incredibly complex system and look for signatures. And I also like to say, by the way, that that we have progressed from Newton, who was obsessed with alchemy, among other things, that we now do anti-alchemy, because I think in general we smash gold atoms together and produce lead. And so and so it's a great progress of science to move backward in that way. Anyway, speaking of progress, I think you wanna talk about some progress with, fusion.
Yes, so there was some news that wasn't hyped, and it was so not hyped that I completely missed it, which
Yeah,
was that the NIF, the National Ignition Facility in the United States, set a new record with the laser ignited fusion. It was like their sixth or seventh shot,
7th, I think, yeah.
where they have, like, I think they have 192 lasers that they shoot out a fuel pellet, and actually ignite fusion in the thing. And I think the first time they managed to do this was in 2022 or something like
Yeah,
this.
2022, that's right.
Yeah, and so now, their seventh attempt was actually a record, and they say they put in like 2 megajoules and they got out 5. So that's a gain of something like 2.5. If you only count the energy that went into the fuel pellet, and that came out, and you neglect all the energy that you had to use to actually get the lasers to run, which is something like 400 megajoules. Still, I think it's really interesting, and I was surprised that, basically no one paid any attention to it. So, and this encouraged me to look up, what else is going on in, laser ignited fusion, and I found out that actually they're building a facility basically over there, in Germany, in a decommissioned nuclear reactor. So the Germans also want a piece of the pie. It's not going to be as big as the one in the United States, but you never know what the Germans will come up with. And the Chinese reportedly have also built one, because there's satellite images of a facility that looks pretty much exactly the same as the NIF, just larger.
Just
So,
larger.
which brings up the question, like, why? If the thing is so inefficient. So if you take into account all the electricity that goes into the laser, that you have, a gain of 0.5% or something. So it's kind of pathetic. Um, but the NIF wasn't built
Yeah,
to
it's, it
generate electricity, right? It was built to shoot at things, like is in the name, basically. Um, and of course, there are newer lasers, there are more efficient lasers. There's also been another experiment at the University of Rochester. I think that's on the East Coast somewhere,
Hmm.
where they pointed out, actually this was known before, but they did an experiment that actually showed it. So what the NIF actually does is they shoot the laser beams into this pellet, which has a gold coating in the inside, and then
Hmm.
the laser gets reflected, and the reflections converted into X-rays, I think, and it's those X-rays that go into the actual fuel. But this procedure, so the reason they do it is that they don't have to aim as precisely.
Hmm.
So I think they call it the Hohlraum. That's kind of a German
Hmm.
word that made it into the literature. That you don't need to fine tune your aim as precisely. This is why they do it. So it's just easier, but it reduces the amount of energy that actually goes into the fuel, which is just something like 15% or so.
Yeah.
And so those guys at the University of Rochester, they don't have enough power to actually ignite nuclear fusion, but they showed that if you do it directly, it's more complicated, but that way they could get 60% of the energy into the fuel pellet. And so this is already a factor 4 higher. And so there are lots of these small things, where you can you can improve a few factors, a factor 4
Yeah.
here, a factor 6 there, a factor 10 there, and then so on and so forth. And I think this is why there is a limited but existing commercial interest in trying to actually create energy from them.
Okay, I suspect it's something totally different, but I just want to I mean reiterate something you said and add something else, which is, yeah, one of the reasons they do the X-rays is this converts energies, and what actually the X-rays do, it's not so much the X-rays. What they do is create an implosion, so the outer part gets evaporated quickly, but because it's so hot, but there's a strong pulse of energy that's going inward, and it compresses things in a time shorter than it would take the whole thing to dissipate. That's why it's called a nuclear inertial fusion. Namely, the inertia of the stuff inside. The stuff inside can't move fast enough because I understand the shock wave is going at 400 kilometers per second into this thing, which is and so therefore a very small fraction of a second in a small drop in a small pellet. And so the fuel can't dissipate in time to actually it gets compressed in a quick enough time that it can then recreate conditions in the sun and have some fusion. But I think the reason that these other that Germany and certainly China are doing is the same reason that the US built it. As you point out, the US didn't build this for energy. It built it for another, and the reason it's done at Livermore and not somewhere else, which Livermore is one of the places where they build nuclear weapons, is that one of the big problems of uh, stockpiling nuclear fusion weapons is checking to see if they continue to work, and you can't. And one way, of course, is to blow them up, which we used to do in the old days. But now, happily, at least for the moment, all nations have a test ban treaty. But another way is to try and recreate conditions is to actually have small fusion conditions and see if fusion pellets get degraded and all sorts of things. So the idea is really for weapons research. It's nothing to do with energy generation. And the other fact that makes it clear that this is not useful for energy generation is what is the fact that you said it's been 5 years. No, it's been 3 years. Sorry, since this breakthrough, of 2022, where they got more energy out than into the pellets, and they've had 7 shots. Okay, and if you really wanted to have a commercial thing, you'd have to be producing many of these things every second. And I've been to the Livermore facility, and it's immense and complex. But, so I suspect China is doing it for the same reason that the US is, which is they wanna be able to check various aspects of their nuclear, stockpile, and maybe Germany also for the same reason. I think, the real nuclear fusion that's going on, and we've talked about in an earlier episode, are these, tokamak kind of things, these magnetic storage things. But it's nice to see. Well, it's not surprising, that's why maybe the reason this didn't get a big. I mean, the original thing got a huge press, I remember, and one had to talk about the fact that it wasn't, the suddenly fusion wasn't gonna be an energy source. This was, getting 2 times the net energy. As you point out, this is the energy going into the pellet, not the total energy produced by all of these lasers. Um, But I suspect that this new threshold, getting it from 2 to 2.5, is great from the point of view of the experiments that are going on, and maybe these other things that'll get more energy into a pellet will make it more efficient, but I suspect that this kind of technology is n is not the technology that's gonna produce power. It's gonna be used for, um, creating fusion in small doses and doing experiments that weapons scientists like to do. Anyway, that's my bet.
So personally, I agree with that. I have said this previously. So I think there are other approaches to nuclear fusion that are much more promising. But so I strongly doubt that the thing that the Germans are building has something to do with testing the nuclear stockpile because we don't have one. So that's the one thing. The other thing is that it's not a governmental project. It's actually a
Oh,
private company, and it's some US-German collaboration. Unfortunately, I forgot the name of the company. Yeah, so I think they actually want to, test out some things
wow.
for their. Yep.
Well, it's great. Well, entrepreneurs, if they come up with something new that works, I mean, everything I know about it suggests it's difficult. Not just the laser and the total power and the small fraction, the immense system you have to create, but even the pellets themselves are not easy to make, and that's why you can't, that's why you have to, you can't plug through 50 of them an hour because it costs a lot to make them. And once again, energy generation is a cost issue, and
Right.
and
Right.
so
Yeah.
so
Yeah.
I
I
wish you that your
totally
this
agree.
German firm good luck, but I wouldn't invest in them, I'll tell you that. Okay. Last, I suppose, given our last few conversations, it would be we'd be remiss if we didn't have one topic on quantum computing. Usually bring them up, and this time I thought I would. Um, and I think again, it's not necessarily something to write home about, but it's a claim, it's a discussion about how a quantum computer simulates a two-dimensional electromagnetic vacuum. And and the idea the basic idea is just that this particular system, there when you have two particles in quantum field theory interacting, there are an infinite number of states of the intermediate quantum field, the electromagnetic field, and therefore, if you want to do computations, you have to kind of truncate all of those things to a finite number and do an estimate, and that's what happens. And with qubits, with two states, you're limited in sort of the number of intermediate configurations you can simulate for a system of n qubits interacting via electromagnetism. And 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 a theorist showed that, well, if you could have a system, not a qubit, but higher dimensional bits that had not just two states, but three states, four states, eventually five states, something called a Q-quint, a five-state system, because a lot of these trapped ions, which are used in quantum computers, actually have many states, not just two. And that one experimentalist in Innsbruck looked at basically tried to use the full five-state system of this Q-quint to try and basically incorporate a larger number of intermediate particle-antiparticle pair states that you might simulate in QED. But again, it's so complicated that in this system you can do two dimensions. You can simulate the QED, the electromagnetic interactions of charged particles in two dimensions, which is a pretty darn simple system as it turns out. But nevertheless, this quantum computer, which uses Q-quints, was able to get some measurements, some simulations that simulated the results of interactions of charged particles with an electromagnetic field in two dimensions. Again, it's nothing worth writing home about, but to me, it does point out a few things. One, that quantum systems are interesting, and more complex quantum systems may be more interesting for simulations. We may not just rely on qubits, but more interesting than that, I think, is the fact that it points out where quantum computing will be most interesting, something we've talked about in the past, which will probably not be for all the things that have been hyped before, not for breaking codes, not for doing this or that, but for simulating quantum systems themselves. And but it also points out how hard it is, that even after all of this stuff, you can only simulate a system in two dimensions. So we're in baby times, and quantum computing is interesting, and it will be interesting for physicists, probably to simulate molecules and molecular interactions they can't do otherwise. but we're still a long way away, even with these Quints. But lots of new work is being done and lots of new systems are being investigated. And the process by baby steps will produce interesting science. And this is one little baby step. So that's why I thought I'd bring it up.
Yeah, now you said everything that I was about to add. So, yeah, no, I totally agree. I think this is like the most obvious application of quantum computers is to simulate quantum systems. That sounds a little bit circular, like you're building a quantum thing to simulate a quantum thing. But the analogy that I like to give people is a wind tunnel into which you put, you know, I don't know, a wooden model
Yeah.
of an airplane to measure the airflow because it's so difficult and then expensive to calculate how the air flows around a thing of exactly that shape. And so I think that quantum simulations do pretty much exactly the same. You know, they give you a controllable model that you where you can, you can change parameters basically as you wish. You can look at it more closely than you could in the real world, so to speak. That has uses. So, for example, one you already mentioned this. One interesting paper that I read like last year or 2 years ago or something. They were actually simulating molecules. So they had it was like a larger version of atoms
Yep.
combining two molecules. And why is that interesting? Because in a real molecule, you can't observe it. It's too fast. It's too small. So you simulate the same thing with a bigger quantum system, and then you can manipulate it the way you want to, and you can look exactly at what's going on. How do those bonds form and stuff like that. I can imagine that this will be good for something.
Oh, absolutely, and I love your wind tunnel analogy. It makes it clear, and I think what even I mean, this was of course Richard Feynman's interest in quantum computing was to look at understand quantum systems, and I think let me push it a little bit more, which is that when you have a molecule of atoms interacting by quantum mechanics, um, you can try and calculate what it's doing, but you're always using classical tools and approximation to the and so, but if you could take a system that m simulates those particles, but does it in a quantum mechanical way, then they're actually doing the calculation. They're actually doing all the quantum mechanics, and therefore doing something that you really can't do, classically, and so therefore they're really allowing you're allowing quantum mechanics to do the quantum mechanical calculations of quantum systems that you otherwise approximate classically. And so for certain systems, and molecules in particular, maybe drugs later on, that's where quantum computers will be very important. And that's I know what Feynman's interest was, which is allowing quantum computers to sort of explain quantum mechanics to us in ways we couldn't understand otherwise. And that was his fascination with it. But it's baby steps, and I'm glad to see this wasn't hyped, but it was it's an interesting little steps. It's not what I was very happy to see was they weren't claiming they were going into 5 dimensions or into other worlds or anything else, any of this other nonsense. They were just doing a more complex calculation, which is itself an approximation of the real world, even under very in a very simple system of 2 dimensions. Anyway, but that's maybe a good way to leave is that once again reminding people that science is often done by baby steps, in spite of the newspapers want you to and magazines only sell things by doing hype, and so they want you to think that every discovery is revolutionary, but baby steps take us a long way, and that's what makes science work. So, thank you once again. I always enjoy your perspective, Sabina, and
Well, thank you.
yeah, as usual here. And I hope you have a wonderful month of May, and I'll see you when the weather's a little bit warmer here. So,
Thank you, thank you.
Hi, it's Lawrence again. As the Origins podcast continues to reach millions of people around the world, I just wanted to say thank you. It's because of your support, whether you listen or watch, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you'd like to see any parts of the podcast improved. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at origins-project.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture.